Then the linking number is linking number of two components of some map of this kind is defined as follows. We consider this map and take a homotopy of it contracting one of these components to a point, or maybe both of them to the to a point. Homotopy, a smooth homotopy of general position, a generic homotopy, during which we several times get the crossings. So one component meets the other one, and we get this local surgery several times. And so we say that for the final link, when one of the components is contracted, the value of the linking number is equal to 0. And for all other links, it is defined by induction according to the following rule. When we pass through such a position, then this number, the linking number, this invariant, jumps by 1 or minus 1, depending on the kind of this surgery, of this passing, which is defined in the terms of the orientation of the ambient manifold. Namely, we consider, well, here in this local situation, we consider the frame of three vectors, one of which is tangent to the first component, the second is tangent to the second component, and the third is defined as follows. We take the first position of our link before the surgery, and we take the point which, after this passing, will meet and go through the other component, and we take the vector of velocity of this point when it goes towards this point, to the point of meeting. So this is the third vector, and so we get the frame. We compare the orientation of this frame with the fixed orientation of the manifold. This gives us the index plus or minus of this surgery, and we say that the value of the linking number before the surgery is equal to plus or minus, is equal to the linking number after the surgery, plus or minus, depending on this sign, plus or minus 1, depending on this sign. So this definition appeals to the orientation of the manifold. More or less, well, a similar situation, a similar construction holds also in a less classical case, in less classical setting. Then the links, these components, are not contractible anymore. They represent maybe some, they can define non-contractible nodes in our manifold. In this case, we can try, usually with success, we can try to define the linking number in the following way. Well, of course, the first invariant of such a link is the union of homotopy classes of both our components. we consider the image of this of the first of the third circle, and it defines some element of the fundamental group of the manifold. Model the conjugation, because we don't fix the point in it. And of course, if for one link the image of the first component defines some element of this set, and for the other link it defines some different element, then of course they are not equivalent, their links are not equivalent, and we don't consider the problem anymore. However, if these elements are the same for the first component and for the second component, then the linking number is defined as follows. The invariant, the similar invariant is defined as follows. We consider this pair of elements defined by the first component and the second component, and we fix some model link representing this pair of elements, and we say that for this model link, the value of linking number is equal to 0, and then we try to extend this linking number by the same induction to all other links exactly in the same way. We take this link, we take the deformation of it to this model. It is possible to this model link. It is possible because they are in the same homotopy class. Then we consider all these local surgeries during this deformation, and well, and etc. No, the element of fundamental group is, it means, well, it means that A is equal to A prime if there exists C, some element of the C, also the fundamental group, such that A is equal to C minus 1 A C. This is just an enumeration of the components of the free loop group. What is the difference from the very classical situation? There are two main differences. One of them is as follows. In fact, in this case, the discriminant, yes, this is the key word of our talk. The discriminant is just the subset. The discriminant, let's denote it by sigma, is the subset in the set, in the space of all maps. It is a union of such maps which actually are prohibited. It is a set of maps of this union of circle such that there exists a point x in the first circle and the point y in the second circle, such that f of x is equal to f of y. It is a set of maps which are not links, the singular links. So it is easy to see from the previous definition that the linking number can be considered as the linking number in this space with the discriminant. So we consider this space Of course, it is infinite dimensional, but we will consider it. It is possible by some argumentation as a by some argumentation, this finite dimensional approximation. We can work with it with a finite dimensional space of a huge but finite dimension. And then we consider this space. It is not a vector space. It has some topology. And so we have, in this space, we have the distinguished point, which is a trivial link. And we have the point which corresponds to our link. Then our homotopy, our deformation from the given link to the trivial one, is some path from our point this to the model one. And the linking number can be defined as the linking number with this submanifold. This discriminant is some hypersurface of codimension 1. This rule, which was explained here, defines its transversal orientation. And when we go from this point to this point, then we look all the points of intersection with the discriminant, which are exactly the passing through the singular links. And count the indices which correspond, which are defined by the transversal orientation of the discriminant. It is whether we pass from the positive side to the negative or vice versa. And we count all these indices over all the crossing points. And the sum of these indices is defined as the linking number of this link. So it is the reformulation of all the same in the terms of the discriminant. So in this case, it turns out that the discriminant is more complicated than previously. In this case, the discriminant, well, the components are contractible. The discriminant is irreducible. It is some component of the well, it is a hypersurface. All components of which go, well, actually it is essentially one and the same component, which can be passed several times, but it is one and the same component. In this case, there are many components. Generally, there are many components. Indeed, what is the component of the discriminant? In this case, we see that the discriminant point, the generic discriminant point, is some union of two circles with unique intersection point. So we can take this point for the distinguished point of the manifold, and then we get two elements of the fundamental group. A and B, two elements of the fundamental group of the manifold with the center at this point O. And this pair of elements more or less characterizes the corresponding point of the discriminant. However, of course, if we move this point slightly, or maybe not so slightly, then we should be, then we stay in the same component of the discriminant. And so, in which case, some other pair of elements of the same fundamental group will define the element of the same component of the discriminant. It is easy to see that it will be so if and only if AB, the pair AB and pair A prime B prime are conjugate. They are simultaneously conjugate. They are equivalent if and only if there exists unique element C such that A is equal to C minus 1 A prime C and B is equal to C minus 1 B prime C, where C is the same in both cases. And in general, it can happen that are several such conjugation classes within one and the same component of this. It is a general situation. Then we get several irreducible components of the discriminant, and any of them can, in principle, define its own linking number. If they are here and the model link is here, then we join them and we count separate the intersection points with one component of the discriminant and with the other component of the discriminant and with any other component of the discriminant. All of them can, in principle, define linking number, which are different, sometimes, usually independent invariants. However, there is also another problem here, another novelty, that in this case, in general, such intersection numbers with these discriminants are not well defined as the invariants of the link, indeed. So we have joined our link with this point by some path. What if we join it by some other path? Will we get the same intersection number or not? Generally not. I will give later some example of it. It are some very easy examples. And how to check it? Well, it is very easy. If the linking number with some component or with some linear combination of these components is not well defined, it means that these intersection numbers are different. Then it means that the intersection number of this one-dimensional cycle with the component is not trivial. This means just the following. Any of these components defines a cycle in this space, a cycle of codimension 1. We take it is a cycle of codimension 1, so by the Poincare duality, it defines the cohomology class of dimension 1. And the non-correctness of definition means only that this cohomology class is not trivial. So the correct way is as follows. We take the linear combinations. We take the union of all components, of all irreducible components of the discriminant, which are characterized in this way. We take, the linear combinations of them. It is the group of all cycles of this kind. And we have a natural homomorphism from this group to the one-dimensional cohomology group of all this space. And we need to take the kernel of this homomorphism, only the elements of the kernel, the linear combinations, such that the intersection index with any closed loop is equal to 0. Only such a linear combination define well the linking numbers. In fact, this is an easy problem because for most three-dimensional manifold, the one-dimensional cohomology group of this of the loop space, actually, of the free loop space is very easy, and it gives us almost no problem, but we should think about it. So it's the classical case, the case of orientable manifolds. And so now let me go to the next, even more non-classical situation of non-orientable manifolds. The case when the manifold M is non-orientable. Then, well, in the case of orientable manifolds, we have this rule to define the transversal orientation. It is the sign of passing through the component of the discriminant. And how to be in this case? Can we, in fact, the counting of the components is the same as in the non-orientable. Again, the components, or irreducible components of the discriminant are in one-to-one correspondence with such pairs of elements of the fundamental group, modulo the simultaneous conjugation. So we can count them, but can we define the transversal orientation of it? How to do it? In fact, we can. Very often we can do it, sometimes not. And how to check it? Again, this is quite rudimentary exercise. And the answer is as follows. Consider some component, which is represented by two elements, A, B. Consider it modulo the conjugation. So this is the notation of the component of the discriminant. This is a proposition. It is not theorem, but because it is very trivial. Maybe even no proposition. So this stratum of the discriminant is not co-orientable. It is no chance to define the transversal orientation. If and only if there exists some element C of the fundamental group which commutes with both A and B. And C destroys the orientation of the manifold. Destroys the orientation of our manifold. Or, in scientific terms, the first Stiefel-Whitney class of C is not equal to 0. So it's main part of theory. So it remains to do the following. We take all the components, all the irreducible components of this discriminant. We choose those of them which don't satisfy this condition. So if some component or the corresponding pair of elements doesn't satisfy this condition, if there is no such C, then we can still define the transversal orientation, even in this non-orientable space, in this non-orientable manifold. Then we select only those components which don't satisfy this condition. We take all linear combinations of them. All these linear combinations define well the one-dimensional cycles in this space, and we can again try to define the linking numbers with these linear combinations. And again, we need to check whether this definition will be correct. It is whether such a linear combination doesn't define the non-trivial one cohomology class of this space. So It is almost all of the theory. And now just several examples.
The discriminant stratified set.
Yes, it is stratified. Yes, it is stratified set. It is stratified set. But now I consider, well, it is stratified set, and we can use this fact to define many other invariants, more complicated than just the linking numbers with the components of with the irreducible components of the discriminant. But now we consider only the simplest invariants, the linking numbers with irreducible components. Yes, any of these components is stratified. However, it is image. It has a natural resolution. It is the image of a smooth manifold. Any of these components, well, actually all of this discriminant has what is called the tautological resolution. What does it mean? So sigma is a set of F of such maps F, of maps F such that there exists point X and point Y such that something. Then we can eliminate this quantifier, and we can consider the following set. Let's call it sigma. It is the union of triples. And the Cartesian product of the function space F times S1 times S1 such that all the same is satisfied. F of X is equal to F of Y. And, well, this is a smooth manifold. And this condition also is smooth, so it is a smooth manifold. And the irreducible components of the discriminant are exactly the direct images of these smooth manifolds. This manifold, again, say in this case, the components, this manifold can consist of several components, of several manifolds, several connected components, and these components are, well, the irreducible components of the discriminant are exactly the direct images of just the projection of this smooth manifold. So, and this projection is, in some sense, it is proper. So, it's the direct image of the homology class of this manifold defines the dual homology class, and everything is okay. So now just the examples. The simplest non-orientable manifold is RP2 times R1. Unfortunately, in this case, we get nothing. No linking number, no integer linking number can be defined. Actually, the linking numbers modulo 2 are well defined in the non-orientable case, no problem at all. But we use these orientations, co-orientations, etc., to define the integer linking numbers, which define the integer invariants and infinitely many, which can define, separate infinitely many links. So in this case, unfortunately, the fundamental group is too small, and all of this group destroys the orientation. No profit at all. But in the next, already in the next complicated case, when we have the Ticknet Klein battle, we get a lot of invariants which can solve many problems. So, maybe so, yes. Let's consider this Klein, well, this model of the Klein model, and we multiply it by the line which goes to us, and we consider the diagrams of the links in it. So, well, let's denote this generator by A, and this generator by B. A and these two sides go to one and the same side, and these sides are opposite. Then we know that the fundamental group is generated by these two elements, A and B, modulo the obvious relation A equal to what? B, A, B. Everybody knows this group. And now consider the following link. One component is a vertical component representing the element A, and the other is contractible. Of course, as usual, the model link, if one of the components is contractible, then the model link is such one, then this contractible component belongs to some small ball, separated from the other component. So, can we separate this link from this one by our invariant? Not. We cannot do it because, well, if we deform this link to this one, then we get the unique surgery like this. And the passport of it is 1A. Passport, I mean, by passport I mean the pair of elements of the fundamental group which encode the component of the discriminant. So this part, it belongs to the discriminant, and the corresponding component of the discriminant is encoded by the following pair of elements of the fundamental group. 1 for this contractible, and A for this component, 1 and A. Then it is easy to see that, if we conjugate it by A, then A stays at the place, and A goes to itself. But A, the element A, destroys the orientation of this manifold, and so this component of the discriminant cannot define the dual invariant, the dual linking number. So it cannot separate this link from this one. Okay. Then consider the next picture. And again, this link for the model link, the trivial link for which the linking number is said to be equal to 0. And this is the link under the investigation. And of course, if we move this link to this one, then the unique surgery is as follows. It is at the point of the discriminant which has the code 1b, which by the same is isomorphic to 1b minus 1. And in this case, we can check that the co-orientation condition is satisfied. The abstraction condition, which was written here, is not satisfied. We cannot find the element of the fundamental group of the Klein bottle which commutes with 1 and b and with 1 and b and destroys the orientation. It is, well, we know, it is easy to see that all the elements of the fundamental group of the Klein bottle can be reduced in the unique way to this normal form. And all the elements of this kind which commute with B are exactly such elements for which this R, the power of A, is even. And so it are the elements which don't destroy the orientation. And so we get the, this stratum, this component of the discriminant is co-orientable, and we can define the dual cohomological, the dual linking number. We can define well the intersection index in this way of any generic path with this component. So it is some invariant which separates this link from this one. Well, for the third example, let be the following. Again, the Klein bottle. Yes, I had here the homological condition that the dual one cohomology class should be equal to 0. In fact, it is easy to see that this condition is always satisfied for the thicknet surfaces. If our manifold is a thicknet surface, then this homological condition is always satisfied. This is an easy statement. Just two examples more. One of them, all the same. Again, the Klein bottle. And these two links. One of them is obtained from the other by a single crossing. Can they be separated? Yes, they can. At this crossing, we have a component of the discriminant with the code AB. Actually, this one represented by this link, by this singular link, and in the same way as previously, we can see that this stratum is co-orientable. We can define the linking number, which separates this link from this one. Finally, one example, then the homological condition is not trivial and it is essential. This example is as follows. Consider just the orientable manifold. This condition is essential already in the orientable case. Consider the manifold S1 times S2. All these are two spheres. And consider the following link. One component is just the equatorial link running once around along this circle. It is the circle times some point here, say the North Pole. And the other link is contractible. Say it can be some, another component is contractible. It can be, say, some circle in one of these spheres. Then in this component, the discriminant is represented just by one irreducible component. Yes, the discriminant to which we can come from this link is represented by just one irreducible component. It is no problem to define its co-orientability, just because the manifold itself is orientable, then we can use the usual rule. And however, we can see that there is an element of the one-dimensional homology group of this component of links, of this component of this space, which has only one intersection with this discriminant. It is very easy to construct it. It is a it is represented by one parametric family of maps along which this component, this node, stays unmoved, and this circle sweeps out this sphere from, well, as usual, as in the homotopy theory, as a family of circles sweeping out the sphere. Then it meets its intersection exactly one, the point of this link. So we have the intersection index, the intersection number one, and the corresponding linking number is not well defined. It seems that this technique is useless if both components A and B are contractible. Indeed, if both components are contractible, then it means that the passport of the link is just 1, and then if the manifold is non-orientable, then for sure we have some map which sends it to itself, of course, which destroys the orientation of the manifold, and so we cannot have any one component of the discriminant which defines the dual linking number, and so the dual invariant. However, everything is not so bad, because in this theory, we try to define the linking numbers only with the components, the whole of the components of the discriminant. We try to construct the cycles in the following way. All the component of the discriminant should be a single cycle, and all its points are, all the pressings of this component are counted with the same sign, and the jumps of the linking number along all of them should be the same. In fact, yes, in the previous theory, indeed, if we stay in this setting, we cannot define the dual linking number. However, everything is not so bad, because, say, we can look in our three-dimensional space. In our three-dimensional space, we can draw, for instance, the Boy surface. Which also is not orientable. It is the image of the projective plane under some immersion. So we cannot define the linking number in the three-dimensional space, the linking number with this surface. Nevertheless, it surely would be zero. Nevertheless, this surface separates some points from the others because it has self-intersections. And looking at the self-intersections, we can see that we can construct the cycles inside the Boy surface, consistent of the smooth parts of it, in which different smooth parts of the Boy surface enter with different coefficients. Some part with coefficient 0, some part with coefficient 1, and for instance, such a part, well, all this part is with coefficient 0, but these two parts with coefficient 1 and this linear combination separate this point from this point. Actually, it is a picture, and in this case, we also can construct the next step of all this construction, of all this consideration, taking into account the self-intersection of the discriminant, and using this, we can, for instance, using the consideration of the self-intersections, we can, for instance, to solve the following problem. We consider again the crane bottle. And consider two trivial circs in it, two contractible circs in it, which are linked in this way. For instance, oriented in this way. What I say, the machinery which I have described previously doesn't help to separate this link from this one, or from the trivial one. Nevertheless, if we take into account the self-intersections of the discriminant, actually, such points, these two intersection points, or similar to them, then we can construct a cycle inside the discriminant, which separates this link with contractible components from this one. But I don't have the time to describe it.